Okay, thank you, everyone. I'm honored to see so many people in the audience this evening, all very enthusiastic to get your physics lecture. So the title is Black Holes with a Twist, and I was asked not to put any equations into this lecture. So what I've done is I've organized this as a story. So we're going to have sort of a prologue and introduction, and then we're going to have 6 chapters, which will gradually lead us through the research that we're doing here at Heriot-Watt University. So what I want to do is I'm going to give you an introduction taken from our favorite science program, the Big Bang Theory, and I'm going to let Leonard and Penny introduce the topic of this evening's lecture for me. Okay, beautiful. So I think that summarizes basically how we do research in my group. So let me summarize what Leonard is trying to explain here. And the point is that general relativity and hydrodynamics, so the equations that tell you how liquids flow, are at some level equivalent. Or alternatively, another way of saying this is that we can use flowing water to simulate black hole physics. And this is what we'll be talking about over the next 45-50 minutes. So let me start from first chapter, C. So C is the letter with which physicists denote the speed of light. And our everyday experience is that light is fast, really fast. When you flip the switch to turn the lights on, the room is immediately illuminated with light. It's not instantaneous, though, as often thought in the past. It does have a finite speed. It's roughly of the order of 3×10⁸ meters per second. So it's very fast. But more everyday experience, which will probably sound obvious, all clocks are the same. So regardless of whether you're standing still or whether you're running really fast, you don't have to do anything special to your watch. It always tick-tocks in exactly the same way. And what we also know from everyday experience is that speeds add together. If I look at this man throwing a ball, it will throw it with a certain speed. But if I watch the same man run and throw the ball, I will see that the speeds add up together. Okay, so I will see the ball moving faster when the man is actually running and then throwing the ball. Okay, so this is our everyday experience. But in 1905, Einstein had, I think it's difficult to underestimate how amazing and incredible this intuition was. And I don't know about you guys, but the more I think about it, the more I just can't get my head around it. What Einstein realized is that the speed of light, c, is actually the same in all reference frames moving at constant speed. What this means is that differently from the ball, light does not add together, the speed of light does not add together with the speed of the source that's emitting it. So if the man that was running, instead of throwing a ball, was shining a laser pointer, the speed of the light from the laser pointer, seen by me, would always be c. It doesn't add up with his speed. And even more strangely, because this is really against all intuition, is that clocks in relative motion actually are not the same. Okay? Clocks that are motion one with respect to the other do not tick-tock in the same way. So a clock that is moving fast will actually tick-tock slower than one which is standing still with respect to an observer. Now, all this had very far-reaching consequences, but in 1905, when Einstein wrote these equations and had this intuition, he was still rather upset and annoyed by the fact that this was what he called equations of special relativity. What makes them special is that they are only relative to objects which are moving at constant speed with respect to each other. Okay? What he really wanted was something that was always valid. He wanted something, for example, that could describe what happens when you have acceleration. So, for example, when you have an observer which is free-falling in a gravitational field. And it turns out that this problem is much, much harder. It took Einstein 10 years to figure out the maths and the equations that would give him what we now refer to as the equations of general relativity. Okay, so it was a huge effort. But these equations have literally changed the world, the way in which we describe the world in which we live in. And once the equations were out there, it only took someone like Schwarzschild 3 months to discover that there was a solution hidden in these equations that predicted the existence of black holes. What Schwarzschild discovered is that there are regions in space where the gravitational pull is so strong that nothing can escape outwards, not even light. Even light is somehow pulled inwards and disappears forever inside this hole. Now, 100 years, or nearly 100 years, have passed since these equations and this prediction. And black holes have been studied in all kinds of forms and variations. And we basically have a blind belief that these black holes really do exist. They're predicted by these equations. We believe that these equations are correct because we've checked that they are indeed correct. Hence, black holes must exist. But as a scientist, you always have to prove that things exist. You can't just go on blind faith. And so this, of course, raises an obvious question. I mean, do we have any direct experimental evidence that black holes really do exist? And I actually hadn't asked myself this until last year and was very surprised to discover that the answer is no, we don't. Okay? There's no direct experimental evidence of black holes out there. What we do have, and that's what I'm going to show you in the next few slides, we do have, though, some indirect experimental evidence. So it was Galileo who taught us that if we want to look deeper into the skies and look for these black holes or whatever we're looking for, we need to build telescopes. And most importantly, we need to build big telescopes. Okay? This is a picture of Kitt Peak Observatory in Arizona, where I was visiting last year. This is a picture of the Hubble telescope. And I'm showing this picture because this is probably, well, I'd say this is an amazing, truly amazing piece of technology. Okay? There's hardly anything else like it around there, and it's really changed the way, literally changed the way in which we view and see the universe. These are just, I'm just going to show you a few pictures taken by Hubble telescope. These aren't just any pictures. These are pictures taken of the very central region of our own galaxy, the Milky Way. The reason I'm showing you these pictures is because we now believe that at the center of every galaxy, or nearly every galaxy, there is what is called a supermassive black hole. So where better to look than at the center of our own galaxy? So this is zooming further and further in, and basically zooming into a region called Sagittarius A star, where we believe that we have our own black hole. The reason we believe this is actually coming from data collected by the European Very Large Telescope Array, which is located in Chile. And the VLT array has been monitoring Sagittarius A star for the past 20 years. This is an experiment that's been going on for 20 years. And just last year, they released the data showing the motion of 28 stars around this region called Sagittarius A star. This is a graphical representation of what they've seen. These stars are moving on incredibly tight orbits and incredibly fast speeds. The only way we have to explain these orbits is by assuming, and the only object that we know that can attract these stars and force them into such tight orbits is a supermassive black hole. Okay? So we don't have direct evidence. We can't, if we look there, we can't actually see anything, but we see these stars moving around at tremendous speeds. It can only be a black hole. So this brings me to chapter 2, gravity falls. So these equations that Einstein gave us tell us that mass curves space and time. Okay? The interesting thing is that it doesn't tell us why mass curves space and time. We still don't know the answer to that question. All it tells us is how mass curves space and time. And this is both sort of the weakness and the strength, as we'll see, of these equations. So what it tells us, for example, it tells us how the mass affects the way in which we measure the distance between two distant objects. It also tells us how different watches or clocks tick-tock when they're placed at a certain distance within a gravitational field. And our everyday perception of these effects, even if though we don't directly recognize them as such, is what we call gravity. Now, I said there wouldn't be any equations, and I lied. There is one equation, but it's so important that I felt that I had to include it, and it's going to come back over the next few slides. So let me just describe very briefly what this equation is. This equation basically summarizes the essence of general relativity, and if you don't want to get into complicated maths, this is really all you need to understand. This is what is called a space-time metric. It tells you how to measure the distance between two different points. Einstein's general relativity is all about geometry, okay? So this ds squared is telling you precisely how to measure the distance between two points. We have this dt here. This is a time interval, okay? So the way in which we measure the distance between 2 points also depends on time. The most important bit in this equation is this one here. This is dr, this is a spatial interval, minus v, this is a speed, times my time interval. What this bit here is telling me is that space is flowing with speed v, okay? So this is what comes out of Einstein's equations. The way we perceive gravity as a flow in space, and this is why my feet are glued to the ground right now. Space is flowing, being sucked in towards the center of the Earth, and as it's being sucked in, it's pulling me along with it. Okay? In exactly the same way. So this is often called the river model of gravity for a reason. It's exactly the same thing as being in a river. You have some fish trying to swim upstream, but the flow of water is pulling them back down. In exactly the same way, when we try to climb a mountain, gravity tries to pull us back down again. And you can imagine now, if you have a waterfall in your river, what will happen, okay? We all have some experience with this. We know that if we're up here where the flow of speed is relatively slow, here c is now the speed at which these fish can swim, and here they're free to swim around and go basically wherever they want. But as they fall over this gravitational waterfall, they will be pulled over, and the speed of the flow will become much faster than their swimming speed, and therefore they'll be sucked downwards and will never be able to come back up again. This is exactly what happens in a black hole. You have this region on the outside here where the flow of space is relatively slow, and if we're in a spaceship here, we'd be able to sort of go wherever we wanted to. But if you come in too close to this point here, this region here is called the event horizon. This is where the flow of space becomes so fast that it's flowing at the same speed as light. Well, then if you fall into here, into this gravitational waterfall, then you'll never be able to get out again. Not only you, but not even light. Space is flowing faster than light and just dragging it in with it. Now, I said that Schwarzschild discovered that there's a black hole solution to Einstein's equation. There is also another solution called the white hole. And they are basically identical objects. The only difference is that the white hole is the time reversal of a black hole. What does that mean? Imagine taking a movie of space as it falls into the black hole, and then you just play it backwards. And what you'll see is that space will now flow outwards. Okay? So if I'm going to be sucked into a black hole and won't be able to get out again, when I'm in the presence of a white hole, what I will discover is that if I try to approach the event horizon, I'll be slowed down until this point here where I'll have to be traveling at the speed of light if I actually want to reach this point here. But I will never be able to get inside. And it's these white holes which are actually easier to fabricate and create in the lab, as I'll be discussing in the next slides. So in 1981, Bill Unruh had another, I think, I'd say definitely an amazing intuition. Bill Unruh was teaching a hydrodynamics course to his undergrad students. He's writing out the equation. He's a cosmologist, by the way. He doesn't study fluid dynamics as such. but he was asked to give this course, and he was writing down the equations, and all of a sudden he recognized a similarity between the equations that describe the flow of water and the equations that describe the flow of space. And so he came up with this idea that maybe it's possible to make black holes experimentally in the lab. The idea is very simple. We come back to here again. Remember, general relativity doesn't tell us why we have this metric. It doesn't care about that. It does away with the mass. All you need to know is that somehow, for some reason, space and time are curved. Okay? So whether it's a mass curving it or maybe the flow of water, doesn't matter. You have the same physics. This was Bill Unruh's intuition. And the way to do this is relatively simple. You just create or take a river, some flowing water, and you put a hump on the bottom. In the top region here, water will be flowing faster than it will be over here. So what you can then do is, you can take some waves and try to send them back upstream against this counter-propagating water flow. Okay? Over here, the waves will be free to flow as they please, but as they approach, there'll be the hump, there'll be a region somewhere here where they will encounter a white hole event horizon. The flow of the water will be faster here than the speed at which the waves can propagate. So they will be blocked. They will pile up at this event horizon. So let me give a couple of examples of where you can actually see this occurring naturally. This is the example, the exercise to try when you get back home this evening. This is a photograph of what is called a hydraulic jump. That's just a fancy technical term to say that we have tap water flowing out of a tap and hitting the bottom of our bathtub. And what you're seeing here is the water flowing down. When it hits the bottom of the bathtub, it's ejected at very high speed. It's flowing at a speed which is much higher, faster than the speed of the waves on the surface here. So all waves are thrown outwards. It's exactly what you have in a white hole. Anything inside the white hole is ejected outwards. Then due to viscosity, the speed of water will gradually slow down. At a certain point, its speed will be the same as the propagation speed of your waves. And here you see them piling up around this circle here. This is your white hole event horizon, which you can make in your own bathtub at home. Another example. So once you understand how these things work, you see them all over the place. This is the fluke pattern left by a whale who's just flipped its tail under the water. So you have the same kind of physics here. You have the water which is flowing upwards, it's reaching the surface and then being pushed outwards. And it's flowing so fast that it's pushing all the waves out. Waves cannot propagate in this region here. Then the flow slows down, and again you see this white hole event horizon where the waves start to pile up along this circle here. Great, so chapter 3, scissors. What do scissors have to do with all of this? Well, what I want to do in the next slide is describe so by formation, I'm not a cosmologist. I know nothing about general relativity. I've always done laser physics. So how did I get into this business? Well, what I'm showing you here is a photograph taken in one of our labs here at Heriot-Watt University. And what we're doing here is we're shining this very powerful, intense laser beam through the lab. What you would normally expect for, let's say, a low-power laser beam is for this thing to sort of, due to diffraction, to become wider and wider as it moves down the lab. But what is actually happening here is that this beam is collapsing in on itself due to what is called a nonlinear optical effect. Okay? And it's forming, basically it's forming a non-diffracting filament of light. And these indeed are called laser beam filaments. And this is what we've been studying for the past, we've been studying these for several years. And what I'm showing here is, so looking a bit more into detail at what's happening inside these filaments, we realize that you have this hot central core where most of the energy is contained. But then as it propagates along, it's forming this beautiful rainbow of colors. But the really important bit is this very marked and distinct V-shaped tail that we're seeing in the spectrum. And this is a very general feature that is there all the time. Here we're letting more than one filament interact with the other, but we always see, regardless of the other details, we always see these V-shaped tails. What we then realized, looking into more details, that these tails are definitely connected to this hot core region. And even more amazingly, this hot core region is traveling faster than the speed of light. Okay? So that, of course, raises the question, how's this possible? How can something made of light travel faster than light itself? And the answer, of course, is in the scissors. So this is another experiment to do when you get home this evening. I forgot my scissors, I was meaning to bring them along, but if you take the scissors and you close them, as you close them together, you'll notice that the contact point between the two blades travels forwards along this direction at a speed that is much faster than the speeds of the blades themselves. Okay? The blades can go relatively slowly, but you'll see that this point, the contact point, will move extremely fast. And this is precisely what we have here. We have these tails here are basically blades of light, which inside the filament are collapsing in onto themselves. And as they do so, they form this hot core of light, which is pushed along at faster than the speed of light. And just to bring back this analogy and just keep this idea alive as we go along, you can also see the analog of these scissor beams in water. This is a photograph taken on a shallow beach. And you have two waves interacting here, forming this hump, which is moving faster than the speed of the actual waves themselves. And in case you're wondering, we did go to the bother of explicitly demonstrating this. We had to develop a special tomographic reconstruction technique to be able to measure how the pulse was moving through the lab. And here I'm showing 4 different shots at 4 different positions as the pulse moves through the lab. And you can see that the pulse at the beginning has these definite, you can see the blades as they're closing in on each other and forming this hotspot. And by measuring how this hotspot is moving along inside the pulse, we found that it is indeed moving faster than the speed of light in vacuum. So what this tells us is that we can create superluminal pulses. We can actually do a bit more than that. By changing the way in these blades of light collapse on each other, we can actually control the speed of this pulse. We can make it subluminal, superluminal, luminal. We can really do what we want with these light pulses. So this brings me to a chapter where I want to kind of describe in a bit more detail how we actually use these pulses. And what I'm going to show you is a 5-minute video that we prepared that describes a bit of a background and introduces the topic of how we use these laser pulses to create our black holes in the lab.
Black holes are supermassive objects that have a gravitational pull that is so strong that even light cannot escape from them. Hence the name black holes. Black holes are formed when massive stars reach the end of their life. They have burnt all of their fuel and then start to collapse under the gravitational pull of their own mass. If they are large enough, there will be nothing that can stop this implosion, and they will finally collapse to a singularity, a single point where all the laws of physics break down. Surrounding the black hole singularity, there is a region called the event horizon. Outside the event horizon, light can still escape the gravitational pull of the black hole, but once inside the horizon, there is no escape. Another way of seeing this is to visualize gravity as creating a flow in the fabric of space. Under the effect of the black hole, space flows towards the singularity at an ever-increasing speed as it closes in. All objects, and also light, are dragged along by this flow, just like fish are dragged along by the flow of a river. When the flow becomes faster than the speed of light, then escape becomes impossible, just like fish cannot swim upstream if the water flow is too fast. In the early 70s, Bekenstein and Hawking realized that black holes are actually not completely black. They can emit some light. This light is coming from a very unexpected and remarkable effect. The black hole horizon modifies empty space to the point that it literally rips photons, light particles, out of the vacuum. The reason this effect is so fascinating is because it is a beautifully simple example of the interaction between gravity, here represented by the black hole, and quantum mechanics. Building a model of the universe that combines gravity and quantum mechanics turns out to be very hard and has not been done yet. Quantum mechanics tells us that emptiness, what we call the vacuum, is not truly empty. There is a continuous boiling froth of particles that come and go. These particles always come and go in pairs, another result of quantum mechanics. We cannot directly see this boiling froth because it forms a uniform background, what we call a ground state, and we cannot directly extract energy from it. However, close to an event horizon, every now and again one of the particles from the vacuum pair might fall into the black hole, and the other particle might escape. For a person looking at the black hole from outside, it will appear that the black hole is emitting light. This light is known as Hawking radiation. Unfortunately, this light is also very, very weak, and we have little hope of seeing it using our telescopes. However, in 1981, Bill Unruh proposed to create artificial black hole horizons using flowing water instead of flowing space. His idea may seem naively simple, yet it works beautifully well. The mathematics tells us that the horizon generated by a small waterfall in a flowing medium will actually generate Hawking radiation. Since then, many different systems have been proposed to generate a flowing medium of some kind. We use intense laser pulses with energies that are so large that they strongly affect the space in which they propagate. In a gas, they can guide lightning, sparks of electricity. In a piece of glass, they can create an artificial horizon. Indeed, these pulses of light change the refractive index of the glass. This change occurs very rapidly and remains locked to the moving laser pulse. This in turn creates an effective flowing medium. We may then use our skills in shaping laser pulses to tailor the properties of the horizons we generate. This allows us to then study how different kinds of horizons interact with light and also with a quantum vacuum. We can ask ourselves questions such as, can we generate Hawking radiation? And what does it look like? Can we probe the horizon with another light pulse? What happens to it when it approaches the horizon? And are there any technologies that may use these artificial horizons? These are just some of the questions that we are trying to answer with our research.
Okay, so what I'm going to do in the following is try to give a partial answer to some of the questions that were raised there. So summarizing very briefly, we have our intense laser pulse, I'm showing you schematically here, which is moving through the medium. And under the right conditions, it will create a flow of space. The interesting point is, you remember the pictures I was showing to you earlier on about showing the black and white hole. On the leading edge of our laser pulse, space will be flowing inwards. Imagine you're sitting on top of the laser pulse. You'll see the glass flow into your face. So this is similar to having a black hole event horizon. And on the trailing edge, space will be flowing outwards, being left behind you. This is similar to this is an analog of having a white hole event horizon. So this is what I was hinting at in the video, and I was saying we can tailor laser pulses and have black and white hole event horizons. So in 2010, we set out with precisely the purpose of trying to see if these event horizons do indeed give off Hawking radiation. The experimental setup is extremely simple. We just have our laser beam just being focused through what is called an axicon. This axicon is just a sort of a conical lens which creates these scissor beams that I was talking about earlier on. The scissor beam is sent in through our sample, and then we're collecting these Hawking photons, this light generated through the Hawking mechanism. We're collecting it and measuring it with a spectrometer. Now, what the spectrometer does is it measures the color of the light that's being emitted. The reason why we want to do this is because when we take Hawking's theory and we apply it to our system, what we discover is that depending on how we generate our scissor beam, so depending on the speed of our laser pulse, different colors of Hawking radiation will be emitted. So what I'm showing you here is a graph where we have the speed of our scissor beam on this axis, and on this axis we have the emitted wavelength from the Hawking radiation, or the color of the Hawking radiation. This red band here shows the predictions from Hawking's theory. These white crosses show the results of our measurements. And as you can see, the agreement of their position along this red band really is a very good indication that indeed we do indeed have a first glimpse of this Hawking radiation effect. So this was published in PRL, but then, of course, it made quite a splash. And as Steve pointed out, it was also publicized on The Economist with the title, Dr. Hawking's Bright Idea. So what I want to do in the next two chapters is give a brief description of where we're now trying to go with this research. I won't have time to give an overview of everything we're doing. So what I tried to do, I just selected two specific topics which somehow continue along this idea that there's an analogy between general relativity, fluid dynamics, and laser physics. The MS Munchen was a cargo ship that disappeared in the North Atlantic in 1978. And it is now recognized as being a victim of a so-called rogue wave. And there have been quite a few in the meantime. There have been at least 7 incidents in the past 10 years. So what are rogue waves? Well, this is a measurement of the wave height taken off an oil rig in the North Sea in January 1995. And what you can see here is this red line shows you the wave, the sea waves oscillating up and down with an average height of about 3 meters. But then all of a sudden, out of nowhere, you get this massive spike, the peak-to-peak height of nearly 30 meters. It's a massive wave. And this is precisely an example. Actually, this was the first ever direct measurement of a rogue wave. Until 1995, scientists didn't even believe they existed. It was thought that they were just sailors' legends. And the peculiar thing about these waves is, like, for example, differently than the other big waves in the oceans, for example, a tsunami, they are very different from tsunamis. Tsunamis are, in fact, very predictable. If you have an underwater earthquake, that's the unpredictable bit. But if you do have an underwater earthquake, then you know exactly what the tsunami will look like. You can model it. You know where it will travel. You know how fast it will travel. You know where it will end up. These rogue waves, on the other hand, we still do not have a way of predicting or forecasting where they will appear. We don't even know the full physics lying behind these rogue waves. On top of that, these waves don't even propagate. They literally appear and then disappear. They just appear from nowhere. Nobody really knows why, and this is what makes them so dangerous. On top of that, they have what is called, so the main sort of feature, identifying feature of these rogue waves is what is called the so-called L-shaped statistics. If you look at sort of the number of waves that you can count with this average 3-meter height here, they will all lie under this yellow hump, meaning that the probability that you have a high wave is extremely, extremely low. But these rogue waves actually appear much more frequently than we would desire. They have this L-shaped statistics, meaning that you can have some few, but not zero counts of waves with extremely large heights. Here are some pictures of some rogue waves. This is a tiny one, but this is what you'll typically encounter. These are massive waves. I mean, imagine seeing that loom in front of your boat. not a nice experience. The rogue waves with heights of up to 60 meters have been reported. And this is the kind of damage that you'll get from even a relatively small rogue wave, which just literally appears from nowhere and then disappears, but in the meantime, it's eaten away half of your ship. So precisely because these waves are so difficult to interpret, understand, until 15 years ago, we didn't even believe they existed. It turns out that the first experiments of these rogue wave events were actually obtained using optics, using laser physics. And these are now called optical rogue waves. But nevertheless, even if they're optical, they're providing very valuable insight into how the water counterpart also work. So these are the results from an experiment that we performed a couple of years ago. Here I'm showing the spectra, or the colors, that are generated inside our filament, our filamenting laser beam. And I'm just adding together all the spectra as we go from one laser shot to the next. And you can see there's a region here, this sort of grayish region. What it means is that at these wavelengths, the intensity of the light is fluctuating randomly and with very high amplitudes. And if I go and look at the statistics here, looking at how high these waves are, I see it has this typical L-shaped distribution, which is the hallmark, it's the feature of these rogue wave events. What we want to do now, though, is look at how these rogue waves interact with a counter-propagating flow. And the reason is because the hydrodynamic theory, or the simulations done with water waves, have predicted that there should be or could be huge rogue wave events in the presence of a counterflow. And in particular, although they didn't realize this when they wrote the paper and they didn't use this terminology, it seems that the rogue wave height will diverge in the presence of a white hole horizon. And I mentioned earlier on, when you start understanding how a white hole forms, you find them all over the place. And indeed, if you look at the speeds at which water flows, for example, in certain areas within the Gulf Stream, these conditions can indeed be met. So what we're going to do, we've got an experimental campaign planned in a few weeks' time. We're going to precisely use laser pulses to create an artificial white hole horizon, and then we're going to be sending in another laser pulse, and we're going to be looking at the rogue wave statistics of this pulse and looking at how these statistics are modified as we approach the white hole horizon. So I want to move on to another topic. This is the last chapter of my story. Title is Cosmic Strings. So let's go back a little bit to this picture that was used to advertise this lecture. This is an artistic rendition of a rotating black hole, and I want to explain why the rotation here is so important. So in a non-rotating black hole, you have your event horizon that's just making everything black here. But when you have rotation, you have another region called the ergosphere, where light is now, you have this, everything is rotating, space is whizzing round, and light inside here is being pulled along at faster than c. What Penrose discovered in the 1970s was a fascinating effect. He realized that if you throw stuff inside the black hole ergosphere, what happens is that this stuff can be matter, it can be light, it can be anything you want. You throw it in, half of it or part of it will be sucked in by the black hole, but another part will be ejected outwards. Okay? Imagine being one of these things that go around, and if suddenly let go, you'll be thrown outwards. But the interesting thing is that the energy of this part of stuff, whatever you throw in that's expelled, will have much higher energy than what you threw in. In other words, we have a mechanism called Penrose superradiance to extract energy out of a rotating black hole. And it turns out, from the calculations at least, that we should be able to extract at least 20% of the black hole energy through this mechanism. So what does that mean? Well, if we just take the energy contained in the mass of the black hole, so it's rather an underestimation, but still we get this huge 10 to the 46 joules. So what does that mean? It's so large it doesn't really mean anything. Well, if you want to make a cup of tea, you need about 10,000 joules. And the world energy consumption is of the order of 10 to the 21 joules. That's a massive amount of cups of tea. But what it really means is that this 20% of your black hole energy contains enough energy in there for an entire civilization, regardless of how many cups of tea they want to make, for, well, what is basically an infinite amount of time. Okay? So I'm not suggesting we should actually try to do this, but what we can try to do, we can make artificial black holes. So is it possible to use this idea to come up with some kind of new technology for laser physics? Can we make an optical black hole amplifier? And when we proposed this idea a year ago, it made, again, quite a bit of a splash and was featured on the front page, the cover of New Scientist. So what we need is a two-dimensional black hole, and we need it to rotate. We need angular momentum. And I keep on insisting, we need a 2D black hole. It has to have 2 dimensions. I want to point out that all artificial black holes, the white holes created to date and studied in some detail, are all one-dimensional. I mean, think of a flowing river of water. This is flowing along one direction, so it's a one-dimensional flow or one-dimensional system. And likewise, in our 2010 experiment, the laser pulse was propagating with a well-defined direction along the piece of glass. So that was also one-dimensional. What we really want to do now is to add in this additional spatial dimension so that we can get this rotation in our black hole. The way we want to do this is we want to literally transform light into water. Okay? And so we want to make what is called a photon fluid. And we can do this by taking a particular kind of nonlinear medium. At low energies, your pump laser pulse will just go through it and won't really see any difference. But at high energies, it will start interacting with this crystal and will expand outwards. And if you look at the equations that describe this effect, you discover that those equations are actually identical to the hydrodynamic equations that Bill and Roux were studying. Okay? So light here is really moving as if it were water. The light intensity is what gives you the fluid density, and the phase gradient on your beam is what determines how your fluid is moving and flowing. So what this means is that if I can control the phase of my beam, I can then also control space-time. Okay, it's an amazing concept. I can control space-time just by controlling the phase of my beam. So this is a picture of what I'd say is a standard laser pulse, which has flat phase across it. But we can take these other kinds of beams where the phase is rotating as you move across it. Okay, it's going from 0 to 2 pi as we go around the beam. These are what are called vortex beams, and they have this rotating phase, and this is exactly what we want. A rotating phase will induce a rotation in the fluid in our light beam. And on top of that, of course, I mean, we can also add in some kind of radial phase, which is the equivalent of sucking space in, just like a black hole would. So this is an experimental picture that we took just last week, where we have, you see the light in the surrounding region here is equivalent, it's basically the top surface of our fluid. If you want, it's the water in the bathtub. And at the center here, you see the singularity of the black hole, and you can see the vortex here, the light spinning round and sucking everything in. And you see these waves on the top, on the surface here, which are moving around. And it's precisely what we want to do now, the next phases of these experiments. We want to monitor how these waves move around and interact with the event horizon, which is sitting somewhere over here, and hopefully we will also be able to measure for the first time Penrose superradiance or amplification from an artificial black hole. But all this talking about rotating phases also got us thinking a little bit more in detail of what we've actually got here. This spiraling beam here has at its center what is called a topological defect. This is very similar. So if the phase is rotating from 0 to 360 degrees as you go around, well, if you ask yourself what's the phase at the center of the beam, you can't really answer that question because it's undefined. And this is very similar to what you have, for example, at the North Pole. At the North Pole, all time zones are converging into one single point. So if you go to the North Pole and you ask yourself, what's the time? Okay, what's the time at the North Pole? There's no answer to that question because you're in the presence of topological defect. Another common place where you can find topological defects is inside an ice cube. In this case, the cracks that you see within the ice cube are due to the fact that the crystalline structure in different points isn't quite matching up. And exactly the same ways you have these cracks in ice cubes, you can have cracks in the fabric of space-time. And these form precisely in points where the fabric of space isn't quite aligning up with adjacent regions. And this is a numerical simulation of what are called cosmic strings. There are these cracks through the fabric of space-time that have formed, or we think have formed, at the moment of the Big Bang. Now, the interesting thing here is that the theory goes is that if you bring two of these cosmic strings into close contact, then there are trajectories. You can move around these strings along trajectories that allow you to have a closed time-like curve. What this means is that you start from here, you go all the way around, you're back in the same place where you started off from, but depending on how you went around here, your watch may have either moved forwards, it may have not moved at all, or it may even have moved backwards. So what we're talking about here is time travel. So the question is, can we mimic cosmic strings using these vortex light beams? This is something we still need to demonstrate. And can we then demonstrate time travel with this? But before going there, we need to ask ourselves even simpler questions, because it's not even, at least not in my mind, it's not super clear what time travel with light in such a situation would really look like. So this brings me to the end. I just wanted to sort of summarize by saying that what I told you this evening is the story of how the geometries of general relativity can be found in rather unexpected and remarkable places. They can be found in flowing bodies of water, in rivers, but then we discovered that we can turn light into water and therefore make artificial black holes even in the lab. But more than that, I think the take-home message here is that we are currently in the situation where we can build in the lab an entire universe. We can reproduce nearly any cosmological phenomenon that we desire. And this is the motivation, the driving force behind the research that we're doing here at Heriot-Watt University. Thank you.